And really just to drive this home, we're going to go to another example that is very similar to this, but we're actually going to add a little bit of extra work before this kind of same loop. And so again, this is softmax, which is also used in AI in neural networks. And the definition of softmax is this expression right here. So for each element in our vector, we are going to take it to the natural log or natural exponent, and then we're going to divide by a sum over all of the elements in the array. So now we need to do a reduction of the array. And so like before, we have this code for all. This is the same code as before, and we're writing our expression here. But now we have this exp sum that we need to compute. And we'll go ahead and look at how that's defined. So in the simple CPU case, or for a single GPU, this is one line of code. And we can write plus reduce and then exp post array. This right here is a parallel operation that will not only expand out this expression, but also do a reduction over all of the elements. And on the CPU, this works. And on a single GPU, this will work. But we want to use as many GPUs as we have in our system. So you'll see that familiar code for all to create essentially one iteration per GPU. And then we'll move the computation to that GPU and do the computation like before, getting our device array and doing plus reduce. The interesting thing here that makes this kind of chapel-tastic is I've got this intent here. So I am expressing my intentions to the compiler with a plus reduce intent. And what I'm saying is this exp sum is going to be summed in this loop. And so by telling the compiler this, I can help it optimize and get better parallel code. So I not only tell it what my intent is, but in a single expression, I get my kernel launch. And then we have our exp sum to then come down here and do our same computation as before. So let's go ahead and run this. And it's going to take a little bit longer, but let's run it with verbose GPU so we can actually see what happens. And of course, print it out. So now we've got a lot more kernel launches going on, and I'll just make this bigger to see what's happening. So again, per GPU, there's 4 GPUs. So everything is duplicated 4 times. And there's this kernel launch on line 40, which is that GPU reduction. And there's also the kernel launch here, which is using the result of that reduction to compute. And while I'm here, I'm going to show one other useful feature. So say you're, developing your application on a laptop that doesn't have GPUs, but you want to write code for GPUs. I've also compiled this code for GPU, and we call it CPU. So GPU, CPU. This is CPU as device, and we're going to basically pretend that our CPU looks like a GPU. And if I run with verbose GPU, you see we still get the kernel launches, and there's only one of them because we're just emulating one of them. But this kind of feature helps if you have a laptop that doesn't have GPUs, but you want to develop your application to work with GPUs. So that's just a nice kind of portability feature of Chapel.